Well, hello. It's been a couple weeks because Matt keeps going camping. So, as it were, it rained on him a lot. So, he's probably not in the
Serve
best.
me right.
So, I am struggling with my camera and the lighting. So, I'm bright pink. Although I am sunburned, I'm not quite this sunburned. And so, I want to welcome everybody to Church Hurdles and remind everyone that the whole purpose of our broadcast or the page or the group, if you're on that in Facebook, is just to help people to basically have a place, a format where they can ask questions and get some answers. And this isn't really about trying to convert people. This is not about trying to convince you that whatever belief system that you currently observe is right, wrong, or otherwise. This is just a discussion. And this has been kind of evolved from my own struggles, which is trying to have questions and getting answers that were real answers and not just a lot of Bible verses thrown at me or something that did not help me understand what I was struggling with. So, a lot of times in my experience, I had found that when I would ask a question, I would get, oh, if you just read your Bible, if you would just have faith, or here, read this verse. And, eventually that becomes kind of dismissive. And basically, the idea was is for me to hurry up and get saved was the bottom line. It seemed like for everyone. So what I really wanted to do was just to have a format forum rather. Sorry, I said format. That allows people to have some questions. To It's okay if you have doubts. It's okay if you don't believe. It's just a place to discuss. And I'm hoping that through that, for people that maybe have some sincere questions and curiosities, that it helps them, and that maybe that produces some more questions, and that leads to great discussion. So I think the biggest thing that we have going on in society today is the I'm right, you're wrong mentality, or us versus them, or me versus you mentality. And really, everybody, can have civil discussions about politics and religion if they just choose to do so. Although I don't see as much of that as I would like. So that's the whole purpose of this. And I was just trying to buy a little bit of time for Matt. He was working on something.
Oh, hey, you can't tell people that.
I'm sorry. I didn't. I'm lying. I wasn't doing anything to help Matt out because everybody knows I would never help him out ever. That would be, you know what, Matt? I would. Turns out this last on my Facebook memories, tons and tons of pictures of our kitchen remodel that we did at my house,
Yeah.
and it was great. Do you remember the duct tape or the masking tape on the walls, putting marking where I wanted certain things, and my amazing drawing that was all sketched out?
I
Um,
remember the drawing. That's the main thing I remember.
okay,
Yeah.
well, I'll have to I'll shoot these over to you so you can see, because I was like, that poor guy. But you did it. It looked. I mean, it came to be. So that
Brought
was
it to
awesome.
life.
Yeah, it's
Yeah.
awesome. So anyway, but so
Well, and we want to talk a little bit about our book, The Case for a Creator by Lee Strobel.
thank you.
Um,
Sorry about that. Forgot.
yeah. So we really have based this whole show off of this book, and there's a lot more in the book. And so if you want to know more, if there are details we don't cover, or if it's you want to go over it again, whatever it is, grab the book, do Lee a favor, um, buy the book, and it is so good. And what I love about The Case for a Creator is, as a journalist, he really knows how to write, and it's just fun to
Mhm.
read. It's just a
It is a
fun
good
read.
read, yeah. And one of the things, the reason that we're utilizing this book is not because like we're getting commissions off of Lee or anything. Just to be
We
clear,
don't even have an Amazon link.
yeah, we don't even. But the thing is that we're using this because this book was really the thing that I had all these questions, and
Right.
nobody seemed to really have answers that were not just patronizing type answers. And so I came across this book and I was like, okay, I'll read it. And I liked it because he's pretty open from the beginning that he wasn't a believer. He didn't really buy into any of it. And unfortunately, to his, perspective, his wife dropped the bombshell on him that she had decided to, to start going to church, and she believed. And well, needless to say, he was like, well, I'll show you. And it's kind of it's an interesting read, because he had a goal in mind when he started looking into some of this stuff, and that's how this book came to be. But for me, it was great because it wasn't somebody saying you should believe because I'm telling you to believe. It wasn't even you should believe because you want to save your soul or any of those things. It was literally, I would read it and I'd be like, that's interesting. And I would think on it, and I would look up look at other resources as well, because I once it piqued my interest enough to move past the, oh, that's interesting point. It turned into something really, really cool. And it's always, there have been some things, even from school. I mean, elementary and junior high, but into high school when we got into really studying biology and zoology and all the other ologies. And I remember thinking how crazy it was that everything worked like it did. It always fascinated me. And that book does a really, really, really good job of tying the two together. So I thought,
Yeah.
so that's one of the things about the book that I think will be helpful for people who, if you're like, I don't even believe in God, that's totally fine. Check out the book and just see. It's not about changing your mind necessarily. It's about getting you to, just like for us or anybody else, to try to see it from someone else's perspective. And that's all I
Get
was
some
trying
data.
to do. Yeah, it had
Yeah.
some really good data in it. So I really enjoyed that book. So,
All right. Well, we're going to kick it off here. And in each chapter, Lee kind of interviews one main person. And so the person that he's interviewing in this chapter is Michael Behe. And I know a lot of times people are introduced, well, he's got this degree and that degree, and I'm not really into that, but it does show that the people that Lee is interviewing in the book, and a lot of creation scientists, quote unquote, if you will, or scientists who adopt the intelligent design view, are not just backwater ignoramuses. This guy has a PhD from the University of Pennsylvania. He's a professor of biological sciences at Lehigh University, also, I believe, in Pennsylvania. His postdoctorate studies, some of them he've performed at the National Institutes of Health. He's authored over 40 articles in scientific journals, contributed to books. This guy knows what he's talking about, and he's not just a real scientist. He's a renowned scientist. He's well known. He's an accomplished scientist, I guess.
where I would be more of a mad scientist, he's like more legit.
Any legit scientist has to have an Einstein hairdo. We know that.
Absolutely. I know. That's why I have to straighten my hair so that nobody's like, oh, she's probably Einstein.
You're Einstein in the closet. You just won't come out.
I know, but that hair, I can't rock it. He was confident.
So Behe really didn't come at this from an angle where he was a believer and just went to prove what he believed from biology. He was taught as a child that God did like maybe create, but then it was up to evolution to make everything happen. So that's what he just took at face value. And as he got into college, he was told that was absolutely true as far as evolution being responsible for bringing the world into its current state. So the more he studied cellular biology, the less he got in the microscope, or the more he got in the microscope, the more he studied that cell, different cells, living cells, the less support he found for evolutionary processes, actually assembling the cells into the highly complex, very efficient biological factories that we have in our bodies and the rest of life. And so for Michael Behe, the how was always missing. Like, okay, we all know evolution's true, but how did it actually bring things to their current state of affairs? And so that led him to ask a lot of questions and actually kind of flip on the other side of the coin. And a lot of these scientists are actually that way. All right. So probably should have already thrown up the slideshow. Our title this time in Church Hurdles and the question, does God exist, is the evidence of biochemistry. And the reason I've got a three-legged stool there, which is really random, is...
It's because you like to sit. That's all.
Hey, that's not nice.
Oh, you're right. I'm sorry. Well, if we take the legs off of it... No, I'm kidding. So
that's it. If we take a leg off, three-legged stool, it falls down, right? If we take the seat off, the legs will fall down, and if they didn't, be really pokey to sit on. So if you just say, if you remove any part of that, then it doesn't work.
It's not functional.
And this is the idea, not functional. This is the idea of irreducible complexity. If you take any part out, if you make it simpler in any way by removing a part, it just doesn't function. So in Darwin's day, this is kind of maybe not even this good. This is kind of what they knew about I'm going to say the simple cell because it's just coming to my lips, but this is what they knew about cells. They could see the cell walls and they could see the nucleus as a kind of blob. If that's all you know, then you might think that cells are the simplest building blocks in the system of life, in living among living things. That this is it. This is the smallest building block. Matter of fact, cells actually have tens of thousands of atoms in them. So it's not the smallest building block by any means. But hey, if that's all you can see, it looks like it.
Sure.
So let's see here. Yeah, we can go to Darwin's Test here. This, by the way, is not even as much as we can see now. You can see the nucleus, but we can see details inside the nucleus. We can see much more clearly the cell walls. And by the way, these were both, as far as I could tell from my sources, these were both mucus molecules or mucus cells.
Rather. So it was snot?
Yeah.
Okay, cool.
Isn't that romantic? I mean, this is science.
And I think we can all relate. Anybody who's ever had a kid, especially, it's like really kids, So, all right.
So,
okay.
You can see these little like worms out from the nucleus. Yeah. You can see little white blobs and dark blobs, and they look different. And if we were to zoom in on this, we would be able to see so much more detail in the simple cell. Darwin's test was, he said, if it could be demonstrated that any complex organ existed which could not possibly have been formed by numerous, successive, slight modifications, my theory would absolutely break down. That's what he said. And although
which I think is admirable, right? I mean, when you think about it.
There's some honesty there. Yeah.
Yeah. Because he believed in what he was seeing. And I always found that really, that's actually something that he said that to me gave his, some of the science and stuff that some of the documentation and things that he produced, a little bit of integrity, because he believed 100%, you know what I'm saying? And he was able to say, this is where this would fall apart.
Yeah. And if this picture of the simple cell, or these three simple cells that we have pretty much fully in the picture, if that's what you know about simple cells, you're not going to think, wow, these are super complicated. There's no way this could have just evolved. He just didn't have the data to look at it. Okay. So the idea here that we're looking at again is irreducible complexity. The example that Behe uses is this mousetrap. If you take out the hammer, the bale wire, I would call it, but the hammer that would actually trap the mouse, well, there's going to be nothing to catch the mouse. If you take out the holding bar, well, there's nothing to hold back the hammer. and on we could go, right? We've got the double spring there, one spring on each side. We've got the end of the spring kind of extended and twisted in a special way where it interlocks with the hammer. And of course, we have to have the trip mechanism there. And we'll notice that these parts, where necessary, are stapled to this board. All right.
You wonder how many times that experiment failed. You know what I'm saying? It's like how many fingers were broken in the invention of the mousetrap.
Man, about break mine just setting one.
I know. That's what I'm saying.
Yeah. So let's see here. I think we can move right on into testing irreducible complexity with the counter arguments. So what we're going to do here is we're going to take this argument that a lot of these cells that we look at are irreducibly complex, that we could not take any part out and they still function. And the reason that's important, I think I've skipped a step. The reason that's important is if you are going to create a cell through numerous slight modifications, then it's going to have to be able to be simpler, right? There has to be a simpler way that it used to be where it still worked, but now it's more complex and better, right?
Mm-hmm.
And so if there's no way for that cell to still exist, with removing a part or with some kind of modification, making it simpler, then there's no way for evolution to be true. That's the idea here.
Yeah. Well, something about that, Matt, if you think about it, it wasn't like cells were like, man, if I only had this. Do you know what I'm saying? Like they didn't think like you and I were like, man, if I just had a computer, my job would be easier. Or man, if I just had, you know what I'm saying, eyes in the back of my head. So that's the other thing I think that was always amazing to me. And I'm talking about even long before I was an adult, and it was always fascinating to me that how did it know? I guess it goes back to what this guy said. The how was the issue. How did it know that that was even an option, right? At all? And how would it know how to make that happen? If it's thinking too bad, because I know the like we'll use eyes as example. Oh, it just started out, it was a photosensitive type cell, and it just continued. But think about that for a minute. We don't the iris, for example, yeah, we know it. It can, it has a obviously allows your pupils to dilate and things like that, but their colors in them, I don't know, that's not necessary for dilation of the pupil.
Right.
There's just little things like that always, from a functionality standpoint. I mean, I love my father-in-law. He was the most amazing man, but he did not care how it looked. He cared how it functioned.
Oh, so he was an engineer.
Yes. So if
my dad was an engineer too.
There you go.
Yeah.
So
yeah.
if that was the case, I would have expected some pretty bland, blobby things, like
right.
You would not think that it would need, again, like I said, it doesn't even know. How would it even know what light and dark are? How does it know? What would it have mattered to it? And so that's always the stuff that fascinated me as well.
So you're touching on intelligent design and the fact that as you look at this, you just see the design, you see the intelligence that was required. And so if you take that away, or it just doesn't make sense. Let me get to my next slide here. Okay.
There we go. We go.
We're not ready for that.
No,
okay, go ahead.
So it looked like a couple of lemons, by the way. Guys, just so you know, we're not talking about lemons. But I think that is, again, though, I mean, this is, when we first started, I mean, of course, Case for a Creator, the whole point in that is to try to, to give people pause to think, well, how did these things come to be what they are and how they are? And for me, again, the whole deal was, it's like, well, how do you explain XYZ? And sometimes it was something as simple as, like when you talk about evolution, okay, well, how similar, for example, certain DNA's structures are between us and other species, right? But when you want to substitute a human heart, you use a pig. I mean, we get pig hearts, pig valves. I like
Right.
bacon. I don't know if that counts, but I mean, that's the thing. It's like that is not. I mean, I understand probably from it, but if you look at a pig and you look at us, you're like, yeah, I'm not really seeing the similarities there. I mean, for some people, I mean,
Right.
maybe, but I've always found that really fascinating. But the bottom line is that what do mammals all have? We all got a heart, we've all got a spine, we've all got a there's a common theme in those because that model works
Right.
really well.
Right. And the hearts that these mammals have are specifically tailored to each
Yeah.
species. Turns out, oddly enough, a pig heart is really similar to a human heart. It's one of
Yeah.
the more similar ones to humans. And the thing, though, is that it's a little different, and it needs to be,
Yeah.
and it's specialized to the hog. And yeah, we can take a valve out and stick in our heart. It just doesn't work as well, and we um, have to take medication and so on and so forth just to make that work. So, but
Yeah.
yeah. All right. So let's test this irreducible complexity. Can't take a part out of the mousetrap theory to see if it works. The first objection is I better bring back up my notes here. The first objection is that a mousetrap could work with fewer parts. So irreducible complexity is false. So in other words, instead of this mousetrap we have on the screen, we could put a different mousetrap up there. We could just dig a hole and let the mouse fall in it. It'd be simpler.
Well, wait. I'm going to tell you a story, okay?
Okay.
Because you'll love this. So in school, one of our, I think it was physics class, we had to create some kind. We had to invent something, right? I invented a mousetrap because what's the joke? It's like invent a mousetrap. Okay, so, but I was a sick kid. I'm just gonna. That's a disclaimer. So
Okay.
my mousetrap was a box, and there was an entrance, and inside the entrance was a teeter totter. Because what? Who doesn't love a teeter totter, right? I'm like, oh, the mice are gonna dig this. It's gonna be great. So they go up the teeter totter, right? But the pivot point was set so that it would pivot, right, which would put the mouse now down into the bottom of the box. But wait, there's more. I had taken push pins and pushed them all up through the bottom of the box and made this giant pad of really sharp needle things for the mouse to fall on. And the more he struggled or moved, the more stabs he was going to get, right? So
should you be admitting this on the air?
Hey, I think I got a solid B on that one. So I think gore was definitely something where they were like, it's a little too much, but it would have worked. The thing is that when you talk about mousetraps, this is one design of a mousetrap, right? But
Yeah.
I have a different kind. Like I've got one out at the one of the outbuildings at the cabin, and it is a plastic, so it's not a wood, but it's a plastic one. But the concept didn't change. The concept is there's some kind of lure to get it to go to the tripping point, and then it smashes its little head, and there you go. So there's a new one out nowadays that they're testing where they get electrocuted instead, because apparently that's more humane. I don't know if I agree with that necessarily, but the bottom line is you lure them in and you kill them. Those are the factors here. This was just one way to do that. And again, this kind of goes back to the variety, right, of species that we have, the variety of everything that we have. So yes, I guess there are arguments that you could take parts away from here and it would still quote unquote work, but the fact that it works is really the key. If you can only take it you can only take it so far back before it's just you're like, oh, here's a piece of wood, it says Victor on it. And they're like, go on, little mouse. And they're like, oh no, Victor. That's
By
not
the way, we are supported this by Victor on this session. Just kidding,
right.
not really. The other thing is, it doesn't matter if you can have a simpler type of cell. The thing is, we're looking at the cells that we have. This is what we've got under the microscope. So the fact that it could be simpler is really irrelevant.
Yeah.
Here's what we have. How did we get it? And
The
if we take away
cell, the simplest cell though still has all the critical factors.
Right. You've got to have DNA. You've got to have ribosomes to make the parts, to actually create the parts of the cell. When it reads the DNA, the RNA, whichever part goes over there, you've got to, and so you've got to have all of these different, you've got to have the cell wall, you've got to have the nucleus. And if you take one of those parts away, it dies.
Yeah.
Because it can't do something that's necessary to its survival. So yeah. Second, second objection that we're going to look at here is perhaps the components of the irreducibly complex, and we'll look at these molecular machines. This is what we're going to look at in a moment, like cilia and flagellum and all these things. So we'll get into that in just a minute. But maybe the components of these irreducibly complex molecular machines developed somewhere else in the cell, and then kind of came together in the right way by time and chance to form this machine that does what it does. The problem with this is it doesn't explain how those parts then were assembled into a propeller that moves that cell through the fluid that it lives in, or whatever the case may be. It doesn't really explain how the machines were put together. I probably should read a little bit in the book because I can't do this justice. So let's see here. He says, but the issue remains, can you use numerous, slight, successive modifications? And remember, that was Darwin's criteria. Yeah. That's a quote from him. Can you use that kind of evolution to get from those other functions? So these different parts of the machine, wherever they're located in the cell, they had an original function. So successive slight modifications, can that move, that piece into this new machine that it's going to be part of? How would that account for that? Can that work? He says that the person who offered this objection, he says he's starting from the finished product, the mousetrap, and disassembling it and moving a few things around to use them for other purpose. Again, that's intelligent design. So when we just even to come up with this theory, we're reverse engineering this machine and saying, well, maybe here's how it got made. Well, that requires intelligent design. But to move on, let's see here.
Well, he once says it's completed, right, Matt? Once it's completed, then you know what the end result was intended to be. But prior to that, I mean, if I just said, here's a board and here's some metal, you would have no way to know what, I mean, unless somebody said and you knew what a mousetrap was, but you would not.
It's like a remodel.
Yeah.
Somebody's got to draw the picture on the wall. And then I know what to build. Absolutely.
Yeah, exactly. And I don't know if that was an intelligent design, just so you know.
Absolutely. But it is. It totally is. I know you're being self-effacing. That's cool. You're being humble. But yeah, there was thought that went into that. And I could not have guessed what was in your mind without some kind of communication. Yeah. Absolutely. Right. So. Okay, and so he says you still have the problem of how the mousetrap becomes assembled. He goes on, when people put together a mousetrap, they have the disassembled components in different drawers or something. They grab one from each drawer and put it together. So you have the parts, and then you assemble them, right? He says, but in a cell, there's nobody there to do that. Well, obviously, right? It's not something humans are making. So he says, no, let me go ahead and read this part too. In molecular machines, components have portions of their shape that are complementary to each other, so that they have to connect with each other in the right way. A positive charge can attract a negative charge. An oily region can attract another oily region. So if we use the mousetrap as an analogy, the one end of the spring would have to have a certain shape or magnetism that just happen to attract and fit with another component of the trap. They'd have to all fit together that way until you had the whole trap assembled by itself. So he says, in other words, if you just had the components themselves without the ability to bring the other pieces into position, you'd be far from having a functioning mousetrap. Nobody ever addresses this problem in the evolutionary literature. Now, remember who's talking. This is not Matt who's talking,
Right.
who's just trying to get these ideas in his head. This is a guy who is a scientist in the field. By the way, got his degree in the 70s. If you've stayed current for 40, 50 years in the field, you know what you're talking about. So when he says evolutionary literature never addresses this, you can know it doesn't. He's going to have a great grasp on everything that's out there. He says if you do
real quick before you on that next part, one of the things too is, and you kind of said it without saying it directly, is that you and I as humans, right, as a whole bunch of cells put together here in a smooth machine, if you will. I'm a smooth machine, but so the thing is think about this. Humans are like, okay, I know that wire exists, or I know that this item, how, cells aren't like, man, they can't think about things that they don't have that, obviously.
No creative power.
Yeah, I mean, sorry, but cells are just like, yawn. I mean, let's do something cool. But I think it's, if you think of it in that context, you have to know that there's something, like a cell doesn't have Google. I mean, maybe they have like cellular Google. I don't know, but
they don't. You're right. They don't.
So it's not like they can be like, okay, I need to fix this problem I've got. How would it even, for example, how would cells even know that they needed to be appendages, or that's stem cells? That's an amazing fact too, which I know I'm getting off track on that one, but that's a crazy notion until if you don't really understand what a stem cell does. I mean, a stem cell is literally, you talk about clay in your hands. I mean, that literally, right. And somehow something had to, but we're not all, we obviously evolve, if you will, even, from conception into whatever. But how does that cell know to be a finger or a nose or a wrinkle, or that is fascinating to me. That has always been fascinating, because something has to tell it to do that. And
exactly.
That's, I mean, that was I think actually when I was reading that book, that was a thing, the section where he talks about DNA so much was so fascinating to me, because I was like, I have kids, and, it was like, yeah, I mean, how does it know to do, and it's not just humans. I mean, we're talking about everything. How does it know that a dog needs to have the little toe pads, and and this dog needs to have this kind of a tail, and this, I mean, it's just amazing to me.
It is. So he goes on. He says, even with small machines, and to bring it back to the cellular level here, how does to extend your point, Susie? How does a cell know, if I could just move around, that would be better for my survival?
Right. Yeah.
How does it even know that? And then, okay, just happen to grow this tail that acts as a propeller and is the most sophisticated machine ever. Wow. How? So, but he goes on from that point and says, if you do any calculations about how likely this could occur, that's not the way I would have said it, but if you do any calculations about how likely this could occur by itself, you'll find it's very improbable. Even with small machines, you would not expect them to self-assemble during the entire lifetime of the Earth.
Yeah, I mean,
that's kind of a problem for evolution. Now we're going to have to blow up the lifetime of the Earth. Now it's not what are we up to now? It's 11, 22 million, or no, it's just 400 million years, I believe, is
I
what we're
don't
up to.
know. My calendar reset, so I had that Mayan calendar. I really want my money back. Hasn't been good for like years now.
Oh man, yeah. So the problem is the you can't get these things to self-assemble chemically, biologically. It just doesn't work. All right, well, let's get into some of these examples since we keep talking about them.
No.
Our first example, well, these are our first two examples. We're going to talk about cilia. That's on the left, and these are really, really big cilia. They're really
Yeah.
magnified. They're not in proportion to the cell.
Look at the little.
Normally, this would just
It's
look,
got a smiley face there, like in the middle. It's like, hey, I'm
that's the
gonna
kidney.
party. Yeah, it looks like yeah. It looks like a
No,
tumbling tumbleweed.
so the cilium would just be like a fur on the outside, a very tiny fur. So these are exaggerated cilium um, hairs that are sticking out here. And
Right.
the purpose is to move. Let me just read a little bit about that. It says cilia are whip-like hairs on the surface of cells. If the cell is stationary, the cilia move fluid across the cell's surface. For instance, he, being B, he said, you've got cilia lining your respiratory tract.
Mhm.
Every cell has about 200 of them, and they beat in synchrony.
Yeah.
So just like centipede's legs, where they're doing the wave, they're doing the
Mhm.
wave, and they're
Yeah.
getting that mucus, uh, sweeping mucus towards your throat for elimination. So that's how your body expels little foreign particles. You get dust in your throat, something, it's going to get caught in the mucus, which is continually being swept toward the throat and coating the throat and moving down the throat. Why? Because of these tiny hairs on all of these different cells.
Right.
So it brings another level of intelligent design to it. Not only are these amazing little machines inside this or attached to the cell, a part of the cell, but these cells are part of organs, and these tiny cells are all working together so that the organ performs the function that it needs to.
Mhm.
Pretty mind blowing. Just too many levels here.
Well, and also, you know, okay, so let's step back just to what we were talking about just before this slide. Just for kids that are watching at home, although we know there are no probably, but the
My
little
son watched it.
oh, okay, so kiddos, just so you know, there aren't little monsters with green hairs or whatever running around inside you. These are very tiny little guys. But what I was going to say is, going back to what you were saying before, again, how would it know? Gosh, if only I had little whip-like hairs and we could all be in synchrony, like a marching band, and then we would be able to just put this mucus or this fluid that we need to
Yeah,
live. We need that moisture or whatever to live, right? I mean this.
right,
I mean there's so many more levels. This is we're talking about this, but that cell has to be able to survive itself, right? It has to
right.
have. I mean, it needs all the things chemically, biologically, all of those things in order to continue to live. So it can be part of the Rockettes band and keep kicking their little legs all in in order there. So
Synchrony.
yeah, I mean it's just think about that though. I mean again, the cell didn't think, oh, if I could just do that, man, what wouldn't that help a lot? And it just and what did it start with? Like, okay, it was like, okay, guys, let's just try this out. And so you get one, the one's just like, whoo, and he's like, okay, if I just had
That's not going to
another
work.
one. And at some point it had to say, okay, that's exactly enough. Stop evolving. Stop evolving.
200 is the right number. Stop there.
Yeah, exactly. So at some point it had to say, okay, that's all I need.
Yeah.
Again, it doesn't, they're not thinking like, I mean, maybe they are. We just don't know that yet. But that's the point is that
There's this problem. They don't have brains and
well, the thing is that it would have to also can somehow stop itself from evolving.
right, right. Yeah. He said cilia also have another function. If the cell is mobile, cilia can row it through a fluid. It
Mm-hmm.
can make it mobile.
Mm-hmm.
Sperm cells would be an example. They are propelled forward by the rowing action of cilia. So I think maybe I've heard the idea that the flagella on the right is kind of how they do it. Well,
Yeah.
apparently that's not the correct idea. It's these cilia all over it that then row it through the fluid.
Oh, okay.
Let's see
And
here.
you know what? Just on that topic, the other thing that's fascinating to me about that is that once it's done its job, how it knows what its job is beats me, but it knows, right? And
Right.
and then the tail, it goes away.
Right.
It's like, it's like, okay, I don't need you anymore. I mean, what happened like the first 3 or 4 times? Like, oh my gosh, the tail is messing everything up, guys. We need a way to just like get rid of that. Can we just have it go away? Like when they send up the space shuttle, right? And they have to let those fuel
Booster tanks, whatever.
yeah,
Yeah.
the booster tanks have to fall off, and it's like,
Yeah.
how many millions of attempts was it? Like, this tail. I don't understand. Everything that gets born has all these weird tails sticking out of it. We got to get rid of the tail. So I just always thought that was fascinating too. It's like, how does it know? It has to come out. It has to do it at the right time,
Yeah.
And how does it even know it did it? I just think that's fascinating.
Right. And yet it works perfectly.
Yeah.
Okay. It says when scientists examined cilia under a light microscope, not an electron microscope, they thought, oh, they're little hairs. But now that we have electron microscopes, we found that cilia are, in fact, quite complicated molecular machines. And that's my cue to put up the next slide. And you guys, this is simplistic. And actually, that is the wrong picture there. So we'll just skip that and go back to the last one. But really complicated. And it's not just a little hair. And he's going to describe it here if you can imagine it. He says, it turns out a cilium is made up of about 200 protein parts. So Lee Strobel asks him, how does it function? And he's like, okay, I'll try to keep it basic. There are 9 pairs of microtubules. Maybe this is the right picture. Here I am doubting myself in the middle of everything.
It's okay. I'm getting something for our producer here.
All right. Well, good.
So I'm going to say, when you said that, I got curious. I'm like, what does it actually look like under an electron microscope?
Well, there you go.
And so I am hoping, I'm not promising.
All right. We'll work on that. You can do that in the background. So it has these 9 pairs of microtubules, which are long, thin, flexible rods, which encircle 2 single microtubules.
Okay, I'm sorry. Say it again. It does what? Oh, I see. Okay. Oh, these look like the beard hairs I get. Little chin hairs.
I think it's a lot more complicated than that.
I think you're right. Yeah.
Do yours wave at people?
Well, if I don't get rid of them eventually.
All right. So you have these 9 microtubules, and actually says that they encircle 2 single microtubules. The outer microtubules are connected to each other by what are called Nexon linkers. Craig, if you've got a better picture, just overlay it on.
So, okay, so
on top of this, we'll go from there. Yeah.
So on the left there, so the 2 little, I'm assuming the green is our little. There's really one thing there, but inside of it are two little things, right? Is that what you're trying to say?
Again, I'm not 100% sure that I have the right diagram, so I'm just gonna.
Oh no! I mean, it looks like it says primary cilium structure. So.
Yeah.
I mean, I'm digging it.
And then there's, I guess, what you could look at is the C diagram. In the gray on the bottom right, you have all of these microtubules, and they kind of surround the A and the B tubule. You can see one highlighted in pink, the other one highlighted in yellow.
Okay, yeah.
And so you have those microtubules around the other 2 tubules inside the cilium.
which to us seems like, wow, that seems like a lot of work, right? Why
Right.
don't you just have one big, you know, wavy thing? But
Right.
that's scientific, right? Wavy thing. I don't know. But again, to us, that seems like, how do I say this? When you look at stuff like this, it's always amazing to me because it seems way, 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 way more complicated than it really needed to be. But the truth of the matter is, this is exactly how it needed to be, which
And it's
is
simple and extremely efficient.
complex as well.
Yeah.
I mean, when you
Yeah.
think about it. So
All right.
that's
So
what
there
these are
are
what they
our
actually
cilia.
under an electron microscope, and these are for the lung. This was what we were talking about,
Ah,
and this has been something they have been trying to figure out now since the 70s to really understand all about how it works. So that was what I found. So
very,
anyway,
very cool.
all
Now the pink and the yellow, I think that would probably be what we're talking about. These dynein um, motor proteins. No. Those would be the Nexin linkers. Wrong sentence. The and that kind of connects those 9 microtubules in each set to each other. And each microtubule has a motor protein called dynein. There we go, or dynein, I think. The motor protein attaches to one microtubule that and has an arm that reaches over, grabs the other one, and pushes it down. So the two rods start to slide lengthwise with respect to each other. As they start to slide, the Nexin linkers, which were originally like loose rope, get stretched and become taut. As the dynein pushes farther and farther, it starts to bend the apparatus. Then it pushes the other way and bends it back. So here's what we're talking about. We got these 2 microtubules with the 9 on each one.
yeah,
And so first this one gets pushed, and then the other
right,
one gets pushed. Boom, you got your,
right, yeah, your swishy tail. So,
yeah.
which interestingly enough, when you think again, how did it know? Okay, who's going to push first? I'm going to try it. Okay, and they're like, no. So again, if it has to, without that, it doesn't work.
Right.
It's the
And
simplest
they all have to
engine
work
ever.
together.
Yeah,
These engines all have to be aligned um, the same direction on the
yeah.
cell, etc. Let's see here. That's how you get the rowing motion of the cilium. Okay. But that doesn't begin to do it justice to the complexity of the cilium. But my point is that these 3 parts, the rods, the linkers, and motors, are necessary to convert a sliding motion into a bending motion so the cilium can move. If it weren't for the linkers, everything would fall apart when the sliding motion began. If it weren't for the motor protein, it wouldn't move at all. If it weren't for the rods, there would be nothing to move. So, like the mousetrap, the cilium is irreducibly complex. You just can't take away any of these parts and have the motor work,
So
have the
how do
thing
you think
work.
it? How do you think that came about? Like, do you think it was like, okay, thinking we need this thing, and then because what you just said, you said it needed to have um the oh my god the connectors, right?
Right.
And
The Nexon. Yep.
yeah, the next, and so it's like, so what did were they there? They just hung out for a while until it was like, okay, we got that piece, but it doesn't really do anything. It's just sitting there. I can't imagine a cell. First of all, how would it know that it needed it?
Yeah.
So it makes it in advance. Like it's like when you like, go ahead and like make your dinners for the rest of the week. It just got ahead of the game, and
And if evolution were true, and this is how it happened, we should have spare parts floating around all over every cell,
right,
just
I
waiting
would
to
think,
assemble into something. And
yeah,
that's not what we see. There
something
is
that,
no
yeah,
trash floating around.
right, yeah. What is that? Just the trash. It'll come. It'll be something someday. So
That's not how it is. All right. Unfortunately, for the sake of time, we're going to move on to the flagellum. And these are very similar. You've got your filament, like a long hair, but it acts as a propeller. You've got a hook that converts that rotary motion into the bigger rotary motion that makes that hair into a propeller. And then you've got all of these parts here that, matter of fact, one of the parts is even called a stator. The little cattail looking thing looks
Oh
like
yeah, I
it's a
see
hot
it.
dog.
Yep.
Or maybe, yeah, maraca something. So that is motor language. You have the same thing in an electric motor, and so you have these pulses that are being given out. You have the rotary motion. Uh, the fact that we would see this in biology in a living creature is it's really kind of nuts to me personally. Um, let's see if we can't get some more details here. It says while cilia act like oars to move cells, it was discovered in 1973 that the flagellum performs like a rotary propeller. Behe explained. Only bacteria have them, so that's why they're called bacterial flagellum. That's the only cells that have them. It says they're extremely efficient. If you picture a boat motor, you can kind of imagine how they work here. Let's see here. The propeller is made out of a protein called flagellin, not to be confused with flagellum. Flagellin. This is attached to a drive shaft by a hook protein, which acts as a universal joint, allowing the propeller and drive shaft to rotate freely. Several types of proteins act as bushing material to allow the drive shaft to penetrate the bacterial wall and attach to the rotary motor. Obviously, a motor or a propeller is going to have to stick outside of the cell wall.
Mm-hmm.
That's a problem because the membrane is needed to protect the cell. So you've got to penetrate it and yet seal it. It says, where does it get its energy? He says, other biological systems that generate movement, like muscles, use energy that has been stored in what's called a carrier molecule, but the flagellum uses another system, energy generated by a flow of acid through the bacterial membrane. This is a complex process that scientists are still studying and trying to understand. The whole system works really well. The flagellum's propeller can spin at 10,000 revolutions per minute. So Lee talks about, as a car enthusiast, he's like, oh, that's way more RPMs than reciprocating engines run at, right?
Yeah.
Matter of fact, most engines, the red line is 6,000-7,000 RPM.
Yeah.
If you turn them that fast, they're going to blow apart. They're going to it's bad. They're going to destruct themselves. Let's see here.
Although you and I have never done that, just for the kids at home, we keep ours at a solid 2,500 RPM.
Pretty much, yeah. It says not only that, he continued, but the propeller can stop spinning within a quarter turn.
Well, that seems precise for something so tiny.
Talk about stopping on a dime.
Right?
Yeah, quarter turn. And we're not done. Instantly start spinning the other way at 10,000 RPMs. Full throttle, reverse,
awesome.
Within a quarter turn.
Yeah. Wow. I bet those big ships wish they had that ability.
No kidding.
Iceberg!
Right? We could have solved the incident in history right there.
Right, yeah.
And the problem is the props would break if you did do that.
Yeah, right. Because the water,
all kinds of stuff would break.
What's interesting to me about that is that if it's in fluid, that it can overcome, right? Because obviously, if you're moving through, like you and I, for example, if we go back to the propeller, the fluid is already moving in a direction, and now you've got to overcome that to also go the opposite direction. In addition, so that's pretty fascinating.
Right. It is. So not only is it the most efficient motor, it has performance specs that are far beyond anything we've been able to create.
How does it know it needs to go the other way? How does it know? Oh, back up! Oh my gosh! How does it?
Well, something has to tell it.
Isn't that neat though? It's like somehow it knows to go reverse.
we don't even touch the control mechanism here.
Right? I know.
But yeah, it's got to have one. It's got to know. It's got to have some instincts built in somehow. All right, so and that really is the mystery, I guess, the biggest mystery of the simple cell. You see it doing exactly what it should do, exactly what it needs to do to survive, and yet, where's the brain? There is no pilot, but it does exactly what it's supposed to do. That's the mystery.
I just out of curiosity while we were talking about that, I looked it up just to see how many cells are in the human body. Now, I don't think there's a
Right.
guy out there going, okay, 1,
What?
2, but they around 37 trillion cells, of course, all different kinds of cells.
Right.
But that's really fascinating because again, you've got, I mean, we just take it for granted because we just come out like this, right? But I mean, you've got skin cells, you got dermal cells, you've got, obviously I mean, the kidneys are just fascinating, I mean, the job that they do. Little bitty, everything is very well defined for its job. I mean, it's wonderful. It's like if your body is the employer, all of your employees show up to work every day, clock in on time, they never leave early. It's awesome.
Always do their work perfectly.
Always do their work. Yeah. They're never behind on a deadline.
Motivate themselves, replenish themselves, energize themselves. Yeah. I can see why this is so amazing now. That doesn't happen. So the flagellum, in closing on that, is about, hang on, I thought I had it.
Uh-oh.
It's a couple of microns, and a micron is a 20,000th of an inch. So what is that? 5 zeros. That's the decimal place, and 4 zeros, and then the 2. And so it's about 60,000 or 60 thousandths of an inch. Got to make sure I'm saying it right. So it's tiny in addition to being amazing. So, okay. Oh yeah, this part was really fun. Behe tells a story about a fellow scientist had a dad who is, let's see, his dad was, I think he was a the dad was an accomplished engineer. I knew it.
I was going to say, I thought he was an engineer.
And he was skeptical as to why his son was so convinced about intelligent design. And then his son, the scientist, put this drawing of a flagellum in front of him, and all of its parts and how it works. As an engineer, he's going to get that.
He understood it.
And if you look at this thing, it looks like something that's right out of an engineering textbook. It's been designed. It's got parts that do specific functions, and of course, it's mechanical, so that helps the mechanical engineer relate to it. So his dad studied it for a little bit, and he said, "Oh, I see what you've been saying."
Right.
That's it. Oh, I see.
Oh, got it. I mean, it is fascinating though, because again, it's one of those things that we think, oh, it's not that fancy. It's not that fancy, like you said earlier, for what we can see of it. Could you imagine, like, if you had I mean, I think that would be something that would be really fascinating. We had microscopes and stuff in school, but I mean, we didn't get to see anything to the degree of like that. If every child or every adult could have their hands on an electron microscope and just be like, I just want to see what that looks like. Maybe it's just maybe they get their own snot bubble. I don't know, but that would be something that, I mean, I think that's just to be able to see how that is underneath all, because we don't think, we can only see it. It's like, oh, that's snot, but you don't think like, wow, I mean, I'll never look at snot the same again. That's all I gotta say.
It's pretty cool. It's really functional. It does what it does very, very well.
Yeah.
So we could talk about some other things, not just these two. We could talk about molecular trucks and highways, and we can only mention these because of time. But there's an intracellular transport system. The cell is not just this bag of soup with stuff floating around in it. You've got to take energy where it should go. You've got to take different proteins where they should go, et cetera, et cetera. And so you have these. Let's see here.
I mean, if you think of the body like a factory, right? That would be like your molecular trucks on highways is all the various departments working together to finalize a product.
Speaking of departments, he talks about this eukaryotic cell or eukaryotic cell. Like cells of all organisms except bacteria have a number of compartments. That's like departments, right? It's sort of like rooms in a house. There's the nucleus where the DNA resides. There's the mitochondria, which produce energy, the endoplasmic reticulum, which processes proteins, the Golgi apparatus, which is a way station for proteins that are being transported elsewhere. The lysosome, which is a garbage disposal unit, secretory vesicles. That's not it. Vesicles, which store cargo before it's sent out of the cell. The peroxisome, which helps metabolize fats. Each compartment is sealed off by a membrane, just like a room has walls and a door. In fact, the mitochondrion has 4 separate sections. And so he talks about there's more than 20 different sections in each cell. And all the new components are made at the central location in the cell called the ribosomes. How do you skip some of this stuff? There's just,
I know,
you need the whole picture.
I mean,
but he goes on to say, this other scientist, Denton marveled, it is astonishing to think that this remarkable piece of machinery, which possesses the ultimate capacity to construct, never mind, that's about ribosomes. You have the challenge now of getting these new components that the ribosomes make into the right rooms where they can operate. And so you have to have another complicated system, just kind of like a Greyhound bus taking people from Philadelphia to Pittsburgh.
Right.
It says you've got to have molecular trucks, which are enclosed and have motors attached to them. This is inside the cells, going from one part of the cell to another. You've got to have little highways for them to travel along. They have to have a path to know where they're going. You've got to be able to identify which components are supposed to go into which truck. After all, it doesn't do any good if you just grab any protein that comes along, because each one has to go to a specific part of the cell, room inside of the cell.
I mean, you can't just pick up hitchhikers, right? What if they're a killer? Like, you got to be careful.
And these are not hitchhikers, right? They have destinations they've got to get to.
No, I'm saying, it has certain stops it has to make, or certain places it has to get, there's a whole process there. They can't just pick up, anything. It has to be the right thing.
And then you have tickets. There has to be a signal attached to the protein, sort of a ticket to let the protein onto the right molecular truck. The truck has to know where it's going, which means having a signal on the truck itself and a complementary signal on the compartment where the truck is supposed to unload its cargo. When the truck gets where it's supposed to go, it's kind of like a big ocean liner that is crossed from London to New York. It pulls up at the dock and everyone's waving, but oops, they forgot the gangplank. So now here's another complicated part. You've got to have a gangplank, a way to get from the truck into that compartment in the cell. Let's see here. So you've got numerous components, all of which have to be in place or nothing works. You have to have a handshake at every part of the system. You've got to have a highway. You've got to have the truck. You've got to have the ribosome producing the parts. The parts have to go to the correct cells or the correct compartments in the cell. He says to me, now does this microscopic transportation system sound like something that's self-assembled by gradual modifications over many years?
And again, I'm just going to go back to, how would it know that it needed those things in advance? So, no.
As it can't.
I mean, it's just fascinating. So, I mean, at the end of the day here, I would love it if people that, if you haven't read, even if you just, or just look up some of the information online or read the sample off of Amazon. But Case for a Creator is really interesting. Even if it's leaving out the religious type of aspect of it, it's just a fascinating read. because honestly, I learned more reading that book and being able to verify the information that I read in it, because that's how I was, especially back then, because I was kind of like Lee in this case, and I was like, well, I'm going to go verify everything I'm reading, which I did. But it was interesting because that was something that I couldn't just be like, oh, well, that's just somebody's opinion. And
Yeah.
I found I learned probably more from that book than I really, of course, I'm old, I was older when I read it, but it was more interesting to me, but I understood it better than I did when I learned it for the first time in school. So, I think that it's an interesting read regardless, from just the scientific standpoint.
So, what I want to close with as we kind of wrap up this series about does God exist is we've talked a whole lot about disproving evolution. And that's important. It's a theory. If it's true, if it's a viable theory, we need to know, we need to accept it and embrace it as the truth. If it's not, then we need to know so we can move on. One objection that might be brought is, hey, okay, so evolution is not true, but how do you know that there's a God? Just
Mhm.
because you disproved a theory that doesn't allow for God doesn't mean that's
Yep,
proof for a God. That's not positive
100%.
proof. So um, I've got something written up here, so I'm going to just read it because if I
Yeah,
ad lib it, it's just not going to go well.
yeah, that's fine.
So here we go. We've also shown, especially in this episode, but really in all of these episodes, that intelligent design is the only answer that adequately accounts for the origin of the world around us, that science is continuing to discover more and more deeply. The more details that we get through our scientific discoveries,
Sorry.
the more it becomes obvious that this is really complicated stuff that's designed well. It does what it does perfectly. And we talked about that. So,
Yeah.
intelligent design, of course, we're still not to the point of a personal creator. So,
No,
um, skipping over part of what I wrote here.
I think it's
But
fine. Just read it.
if there is a designer of the world, then that designer must have had a reason for bringing it into existence. And so that's a huge logical step there.
Mhm.
So this necessarily implies a personal creator being with not only intelligence, but also feelings and desires. A couple of episodes ago, we talked about the Kalam argument, and we touched on the
Yeah.
idea that because the universe didn't create itself, then the cause of the universe must be greater than and independent of the universe. And that really has some informative implications. In other words, what I'm trying to say is you can get a lot out of that. Since the world is physical, then the cause of the world had to be non-physical. It had to be independent and outside of it. It had to be different from it. Okay. Since this personal spirit being created time and space, he must be independent of time and space. And we would say eternal, but that really, in its purest sense, the idea of eternity is just without time. And that's really,
Yeah.
man, that's a stretch for the human brain because we just totally exist in this realm of time. And so to say, well, there is a realm in which time doesn't even exist. That would be the realm where this
Yeah.
spiritual being exists. That's
And of
his
course,
playground.
and for us, and for those that might be not to that level, like you said, either way, I think we're using spirit because that's the term. That's we can't even imagine, right, outside of what we can, our main senses, so that's,
Non-physical.
yeah, so we just can't imagine. But I think it's really, if you can just read some of this information, or even just look it up, just study on it, just be fascinated by it, that at least some whatever we want to use, whatever a person might be comfortable at this point in their understanding be, it's something, it is
Right.
something, because uh you just can't. I'm sorry. I mean, did you guys see that cool thing with the helicopter tail? I mean, that was That's pretty slick, right? So
well, I do want to say what we want to do is we want to look at the empirical evidence from
mhm.
science,
Yep.
and then we can actually go even further with rules of logic to find out
Yes.
as much as possible about that cause. And so, if this is something outside of the physical realm, right, then
Mhm.
it's non-physical. It's a spiritual thing,
Yeah.
and then it had to have a reason. If it really designed the world or designed these cells we've been talking about today, then why? Well,
Yeah.
there's a personality. There's decision making implied there.
Yep.
There's creativity, and so it's a personal
Yep.
spirit.
Yep.
So yeah, and then it's outside of time. It's outside of space. It's outside of
Everything.
all of the things that make up our world, right? So turns out this happens to be the concept of God in the
Mhm.
Bible. So
Yep.
as you think about this, it's an interesting match. So
Well,
that's what I've got.
I agree, and I mean the thing is that that's where I was, however many years ago, with that book. I read it and I was like that. I couldn't just be like, that's because if you really, and I'm not talking about, I didn't go in. Really, I went into it reading like, I dare you, I double dog dare you to convince me because I didn't understand. I mean, I was fascinated by stuff, but I didn't really understand a lot of it. And that book led me to look up other things, find other books, scientific books. If you've never read a book called The Hot Zone, that's an amazing book as well. I believe it's actually I want to say it might be by the guy who wrote Jurassic Park. Did I just probably totally they're like, yeah, okay, the guy with the dinosaurs. I don't think so, uh, but it's by Richard Preston. So sorry, it's not Jurassic Park, but Richard Preston, and it's an amazing book. That is, it takes out. It's not written by somebody from any kind of theological or but it's all about simple diseases, bacterias, viruses, and it's fascinating. And I think I had read that book, and you take that book and then you tie it into this, and it was like, wow. I mean, I had enough, from one that had nothing at all to do with God or intelligent design. And then when I read this one, it reminded me of some of the things I had read in that book and been like so fascinated by how it worked, how it knew what to do what it did
Right.
once it got inside a body. It was amazing.
So, what I'm hearing as you're talking, Susie, I'm hearing someone who is seeking the truth. You
Yep.
cared enough to figure out, hey, what's real, what's not real. And
Yep.
so that's pretty cool. And that's what I think both of us probably just want to encourage everybody to do. Figure it out for yourself. And that's
Yeah.
what this is all about. So
Yep. Absolutely.
thanks for watching. And this is going to be our last episode for a little while, at
Yeah.
least, because kind of, at least on a thumbnail sketch, covered does God exist?
Yep.
And so I think there's enough here to certainly get somebody started on their search. And
Yep.
yep,
I've
so
enjoyed it.
we're
I've
gonna
really enjoyed
take a
it.
hiatus.
And
Yeah,
and yeah, we're gonna take some summertime off. Matt's gonna go camping some more, probably.
let's
Probably
see. I
not.
hope.
But we'd also Craig is our producer, and he's done a great job, and we really appreciate him. And for the 2 or 3 people that have probably watched this, we thank you for that. Pass it on. You never know. We'll get this all smoothed out at some point, I'm sure, and get a little bit, and I'll get better lighting or a better camera. I'm not sure which, or a better face, maybe. I don't know. But again, thank you so much, Matt. I really appreciate it. It's really been great having your insight as well. Really appreciate all the years that you've spent with me on this journey.
It's been my pleasure.
All right.
Take care, everybody. We'll see you.